Hello, and my name is Tim Spiel. I'll be co-hosting this seminar today for the MRL webinar series. We're thankful that you're here. We're going to be having a presentation today from a couple of our staff members. As you can see on the slide here, more info on our webinar series can be found at go.illinois.edu MRL webinars. Today's webinar will be on 3D optical profilometry given by two of our staff scientists, Dr. Julio Soares and Dr. Kathy Walsh. Julio, if you can advance, please. This is a list of some of the recent seminars we've had and upcoming seminars. I'd like to point out we have some seminars on SEM and lithography in the next couple of weeks, followed up by some TEM and thin film deposition techniques. At this point, I'd like to formally introduce our speakers. Dr. Julio Soares came to us from Brazil, where he had received his degrees from the University of São Paulo and getting his PhD in 1997. He's held academic research scientist positions at the University of São Paulo and in the Material Science and Engineering Department here at the University of Illinois. He joined the MRL as a research scientist in 2004 and has been a senior research scientist since 2012. Dr. Kathy Walsh got her undergraduate degree from Wichita State University in Kansas and her master's and PhD at the Michigan State University in East Lansing, Michigan. She has been working with the MRL staff since 2013 and in 2019 became a senior research scientist in the MRL lab. So at this point, I would like to invite our speakers to begin their presentation.
Okay. Hello, everyone. Thanks for joining us today. Thanks, Tim, for the introduction and the opportunity, Mauro, for presenting this webinar. Today we'll give you an introduction to the basics of three-dimensional optical profilometry with an emphasis on focus variation and confocal microscopy. I'll start it by talking a little bit about the concept behind an optical microscope, then introduce the focus variation method for surface profilometry. Then after that, I'll introduce the confocal microscope and how it's used in topography measurements, comparing then with the focus variation method. I'll also mention a couple other optical methods used for profilometry, though we'll not spend too much time discussing them. Kathy will then talk about the data analysis and how to extract numbers from the optical profilometry measurements. She'll talk about situations where the optical profilometry works well and others which are more challenging to apply it, and present some complementary strategies to measure the topography. Finally, we'll offer some final thoughts about the topic. Optical microscopy has been with us for quite some time now, having started in the late 17th century with instruments that weren't much more than a simple lens. The optical microscope has evolved to be one of the most versatile tools used in many areas of science today. Its working principle is very simple. It uses a set of lenses to bend light and to deliver a magnified image of an object of interest, our sample, to our eyes. Most commonly, the object is illuminated either from the top, and we use the light directly reflected from it, or from the bottom, and we'll use the transmitted light through it. Some samples are not very easily visible by direct illuminating the sample. So to observe those, other contrast methods are required. One example of those contrast methods is the dark illumination. Can you see in the right scheme here, in which the sample is illuminated from the sides, and we use the light scattered by it, while the directly reflected or transmitted light is blocked from the detector. Spectroscopic signals like fluorescence and Raman are often used as contrast methods as well. projecting a magnified image of the sample only makes sense if you can resolve the fine details of your sample on the magnified image. I mean, if you have enough lateral resolution. Otherwise, the magnified image doesn't give us any new information about the subject, and it looks just like this, like a magnified blob. Only if we increase our resolution, we can get a better understanding of the objects that are being imaged. The main factor that limits how a fine structure we can resolve from our sample using light is that light is an electromagnetic wave, and as such, it diffracts. When you focus the light as tight as you can, what you get is a diffraction pattern. For the case of a point light source, the shape that you get is that of concentric circles, which we call Airy pattern in honor to George Biddle Airy, which was a mathematician and astronomer who explained this pattern theoretically. The diameter of the Airy disks is a function to the wavelength. And so the pattern that you see from a white light point source will look like a rainbow because the red light is diffracted more than the blue, and so on. Another fact or another factor affecting the width of the Airy pattern is the numerical aperture of our system, which is defined by the angle of collection of the light and the index of refraction of the medium between the object and the optical system. The higher the numerical aperture, the narrower the Airy pattern will be. Our resolution is defined by the minimum distance between two sources at which we can still distinguish them as separate sources. That obviously will depend on the Airy pattern width, and the most universally accepted criteria defining the resolution of an optical system are the Rayleigh and the Abbe criterion. In the optical axis direction, the diffraction pattern formed is more extended, and the axial resolution of a microscope is generally worse than that of its lateral resolution. A concept that is related to the axial spread of the focused light is the depth of field of the optical system. The depth of field is the length in the axial direction in which we consider our image in focus. Now, if we can evaluate when the image is in focus, we can determine approximately how far the object is from our objective lens, if we know our depth of field. For example, in this case with the ruler here, we have the image being more or less focused, or with a good focus between the 20 units and 30 units on the ruler. So if I have a focused object using the same lens and the same camera, I know that this object will be between 20 and 30 units away from the objective lens. The depth of field is shorter with higher numerical apertures, and therefore higher numerical apertures will give us a better accuracy in the determination of the axial position of the object, or a better depth resolution. We can use this to map the topography of the object. As you can see in these pictures, as I move my lens towards the object, different parts of it come into focus. If we track each pixel that comes into focus, we can construct a topography map of the object. And this is what focus variation is all about. And this is the 3D projection of that topography map obtained by focus variation. Two great advantages of this method is that it's fast, and it captures the true colors of the object that we are doing the topography map while we are doing this topography map. As I mentioned before, spectroscopic signals can also be used and are used often for contrast in microscopy, like fluorescence or Raman. Fluorescence, for example, like here, is heavily used in biological studies as it helps identify biological system, specific biological systems or structures using dyes that bind specifically to some structure or another. The one intrinsic problem of this using the fluorescence as a contrast is that the fluorescence from parts from the sample that are out of focus will contribute to the final image as a diffuse background. In 1957, Marvin Minsky patented the idea of the confocal microscope, where a pinhole is placed just in front of the detector. The role of this pinhole is to block most of the light coming from out of focus regions of the sample. The more we close the pinhole, the more out of focus light we block, and that increases the contrast ratio between focused and unfocused light, making the images look much sharper. Besides this increase in the contrast ratio, the confocal microscope also have a slightly increased lateral resolution. In the end, the image quality of the confocal microscope is quite better than that of the wide field, just by eliminating that light of out of focus fluorescence. Here is another example of fluorescence microscopy done on some fibroblasts cells growing on some patterned scaffolds. So yes, adding the pinhole, we get clearer images, but more importantly, the point spread function of the confocal microscope, so that the focus of the confocal microscope is much more concentrated than the wide field microscope, and especially in the axial direction. And this makes the confocal microscope ideal for optical sectioning, where images are collected in a series of focus positions, similarly to what we did on the focus variation technique to form a 3D image. In the case of focus variation, due to the noise added by the out of focus light, it is necessary to detect where what is the best position for the focus of each of the pixels in the image. In the case of the confocal microscope, only the light from a very shallow in-focus volume from the sample makes it into the detector. And then we can just monitor the intensity of each of the voxels of the image across the Z-stack to form the topographic image of our sample. Furthermore, by fitting the intensity variation of that voxel, we can locate the surface reflecting the light with an accuracy of 1% of the Z-step that you use to construct that stack. So here is the previous example that we showed for the focus variation method, captured using confocal microscopy. If we compare the two, you can notice that the confocal has a clear gain in resolution. And note also that this example was done for a large sample with a low numerical aperture lens, which is not where you will see the most dramatic difference in resolution between these two methods. For much smaller samples, this difference will be even more evident. Potential disadvantages of the confocal method are that to form our image, because of the pinhole, we need to scan the point source through the surface, which makes the method much slower than the focus variation. And also, we just get a monochromatic picture of our sample because we're just seeing intensities there instead of getting the full colors at the same time. This is another example where I used the Confocal method to measure the topography of a shallow scratch on a glass surface. Notice that the Z-scale is exaggerated in this picture to show the details of the scratch topography better. This is another example where we can see the topography of a butterfly wing, a little piece of the scales of the butterfly there. A common issue that we encounter, especially when measuring transparent films, is that parts of the substrate can be more reflected than the top surface of the film. If that happens, the software can mistake the substrate surface or whatever is the next layer surface by the top surface, and you get this nice artifacts over there. This image, the top image, was made on the automated mode for our microscope, in which the software decides the range of illumination, the range of the Z stack that it takes, and all these parameters. If we operate in manual mode, then we can try to stick to the range in Z that only gets the top surface, but that doesn't work very well if you have a tilt on your sample, which is basically all the time. It's very, very easy, hard to get sample that is completely flat. So in this case, when I was trying to include the top surface on this end over here, I was already reaching the substrate over there. In those cases, what we need to do is inform the software that our sample is a film, and the interface signal then will be ignored, and we can get the correct surface topography of the top surface. Even better, we can tell the software to capture both, and capture the top surface topography and the interface topography. Whenever you have enough light coming from the bottom surface, you can do that, and you have a good topography for both surfaces there. In this case, we didn't have as much light coming from the interface there, so it looks a little noisy, but with patience, we can do even a better job than that. Confocal and focus variation are not the only methods that are used for optical profilometry. Another one that is commonly used is interferometry. The two main modalities of interferometries that are most used for surface topography are the phase shifting interferometry and the coherence scanning interferometry. These techniques provide excellent vertical resolution, reaching sub-angstrom accuracy in the case of the PSI, for smooth surfaces, for samples with smooth surfaces. They present problems measuring rougher samples and samples with optically dissimilar materials too different of an index of refraction can be also problematic for interference methods. For a more in-depth view of not only interferometry, but all the methods that we mentioned so far, I highly recommend the excellent book by Richard Leach, Optical Measurement of Surface Topography. Several of the images here are from that book. This table gives you a general guidance on how well each of these techniques, methods work for different measurements, conditions, or samples types. In MRL, we have these two types of, these two methods. And here there is a bubble chart that summarizes the ranges of features and vertical resolution for each one of these three methods, which I adapted from a plot at Sensofire's website. Next, Kathy will focus on the details of quantitative information that you can get out of 3D optical profilometry images once they have been acquired.
Thank you, Julio, for that great introduction to the techniques. I'll get into some of the quantitative details next. Now, plotting an image in X, Y, and Z in a 3D display is quantitative, but it's trickier to compare these images visually without having concrete numbers or numbers you can do statistics on. These numbers you can do statistics on are often expressed in terms of surface roughness parameters. Here's an example of a laser barrier curtain, which is made of a plastic material molded on a tightly woven fabric. You can see from this image that the feature here on the right curves upwards in the middle, right? No, actually, this is an example where just looking at it with a really good optical microscope would still lead you astray about the heights of the surface, so optical profilometry is really valuable here. Here we've taken a profile, which is a line just cut through a section of the image, and we plot height versus distance along that line. You can also see the real shape of this laser barrier curtain if you do a 3D representation, especially if you use the color scale to tell you about the height values. In this profile and from the color scale, from Z versus XY data, we can calculate a huge variety of parameters like the heights of the ridges here, or even the radius of curvature of the original mold of this sample. Let's go back to that O-ring example. We can visually compare the focus variation in the confocal microscopy on this sample, but let's make that more quantitative. Notice also that this doesn't look like a circular cross-section, and that's because you can't see through the opaque O-ring. So you can't see the part where it curves back down underneath. And this is the same for all types of surface profilometry, whether it's 3D optical profilometry or stylus profilometry. You can't see around corners or through opaque surfaces with optical profilometry. We can easily measure the height of the tallest part of this O-ring along this profile above the substrate that it's sitting on. And this top surface looks pretty smooth in the focus variation image. But if we switch to confocal, there's a little bit more surface topography there because the confocal is resolving this a little bit better. Note that the software is outputting a number which goes all the way down to the single nanometer height. This is just like when you divide two numbers in a calculator and it gives you all the digits the calculator can give you. You need to think about which digits are significant. Remember that for confocal, the vertical resolution is about 1/100th of the z-step size. And if you're measuring something this tall with confocal, you may even be skipping steps to save time, which limits the vertical resolution even more. The best resolution we could get is probably around 20 nanometers. So even though the software gives you a bunch of digits, don't quote it to the nearest nanometer because it's not significant. But as Julio mentioned earlier, this image was taken with an objective lens which had a low numerical aperture, so the precision is actually much less. You get slightly different peak height values here, depending on focus variation or confocal, which method you choose, because the confocal is giving you more details of the top surface there. But if you just want to know if the O-ring really is 1/10 of an inch thick, use focus variation to save time. If you need to know those surface features of the top surface, though, choose confocal. So speaking of surface features, let's talk about roughness. There's not one absolute number called the roughness, which is universal and everyone uses and works for every sample. You have to think about the surface topography on your sample and the size scale of the roughness that you're interested in. In this analogy, there's variation in the surface topography due to the heights of these flowers and also due to these rolling hills in the background. So by analogy, are you interested in things like single asperity contacts on MEMS devices? Or are you interested in tool wear on large scale tools? If you're interested in those really small contacts, then a different technique is probably better for you. Atomic force microscopy gives you really good resolution on the true nanoscale, a few nanometers up to hundreds of nanometers. 3D optical profilometry really comes into its own around the upper tens to hundreds of nanometers, and it's great for things in the micron range. Whichever technique you're using, make sure that you choose a field of view that gives you enough information. If I wanted to build up this entire image, if I took a very small field of view, I couldn't just choose one. This is not representative of the entire image. I'd have to do a lot of measurements. Also, think about both the resolution of the technique itself and also the pixel size you choose to choose an appropriate number of nanometers per pixel or hundreds of nanometers per pixel that matches the feature scale that's relevant to your roughness measurement. The most common roughness parameters that people use are the average roughness and the root mean square roughness. These are represented with R for profiles and S for entire 2D surfaces. RA, RQ, RZ are the most common. We'll talk about Z later. Depending on the properties of your surface or depending on what is conventional in your field, you might choose RA versus RQ or a different roughness parameter entirely. And there actually is often a significant difference between these two values for certain types of samples. This is one particular example where the average roughness is actually 0. So if I have two features with the same spatial periodicity, on two samples with the same spatial periodicity of features, but just different amplitudes. So here's a red sample in front of a blue sample, and the blue sample has taller peaks and lower valleys, but they're both sine waves. The peaks and the valleys cancel out to give the same average value. But if you take this sine wave shape at the top of the surface and square it, and then take the average and then square root it, you get a positive number. So you will have an RMS roughness that's different for these two surfaces, but the average roughness is still 0. Any surface profilometry software will calculate these basic roughness parameters. But this is another example where you have to think about what the instrument is telling you instead of just taking the number as some absolute truth. You can't directly compare the numbers that you get from images that are taken with different resolutions unless your features are much bigger than the resolution of the instrument or much bigger than the feature size. Make sure also that you're telling the software to ignore large protrusions that are not actually part of your sample, like dust that's landed on the sample or parts of the sample that have broken off and you want to exclude. And you do this by masking, which is telling the software what to ignore and what to include in its calculations. You can also use masking to compare results you get in different parts of the same image, for example, in the brown part and the blue part here. These areas may have different surface morphologies, so just getting one roughness number for the entire image wouldn't be very helpful because we've got two pretty distinct areas here. You should also try multiple areas on a sample, especially if your sample is inhomogeneous, because there will be small variations and you're building up statistics on the roughnesses of your samples. Let's look at two completely different areas of this same butterfly wing, which are clearly visibly different. This part is brown and blue. This part is sort of a different brown and has maybe some more lumps in there. And because of this, when we compare them, we'll divide each area of the image into, each image into 4 separate areas. And that's so that any differences we calculate between this image and that image are not being overshadowed by the differences between, say, region 2, which is blue, and region 3, which is brown here. Then the software will calculate the roughness parameters for each of those quadrants and compare them between the two images and find out which is most significant. And this is a really nice feature of the analysis software on the Keyence instrument that we have here on our 3D optical profiler at MRL. The most significant one in this particular case, where the distribution is very different in both of these images, is S sub Z. If we were doing a line profile, it would be R sub Z, and Z is the difference between the highest point and the lowest point on your surface. This is one of many, many, many roughness parameters, and others that may be relevant are longer scale roughness features. For example, these hills in the background. This is waviness, which you can either choose to measure or you can choose to exclude as a background if, for example, you're only interested in the flower heights on this hill. The S sub Z, the peak to valley maximum on the sample, is one parameter that is one of 2 height-related parameters that have to do with whether you are able to safely measure this in your instrument or not. Whether you're able to safely measure your sample in the instrument, the first factor is pretty obvious. Can you even fit it in the instrument? And the answer to this is almost always yes. Most 3D optical profilers give you a lot of physical range. We even fit in a whetstone once when during an instrument demonstration from some of our colleagues in the archaeology field. The other Z parameter is a little more subtle. This is comparing that S sub Z, the highest point on the surface, to the lowest point on the surface, to the working distance of the objective. Here I'm comparing two different objectives. One has a working distance of 8 millimeters and change. The other has a working distance of about 16 millimeters, so roughly a factor of 2, even though the magnifications are different. So if I want to focus on a feature at the bottom of this, this sample here, then the 8-point-something millimeter working distance objective has to get closer and runs the risk of crashing into features that protrude on the sample. Now, not every sample is flat on the bottom and just has its surface roughness making a difference. Many samples are tilted or even curved. And depending on what you're interested in, you may actually want to exclude this from the calculation. Even if your samples aren't curved, they're almost always tilted, at least on the nanoscale. So you have to correct for this in order to get a reasonable measurement, because otherwise the S sub Z is going to be way too large and it's going to affect your roughness values. So let's see that effect on our O-ring example again, which has a radius of curvature of about 1.5 millimeters, which is pretty large. If we look at the roughness values of just this small section of the top here, we're getting an R sub Z, that's the tallest point to the lowest point, of 180 something microns, which is pretty big. But that's pretty much all being dominated by this curvature of the O-ring underneath. So if we subtract that, you come up with just the roughness due to the surface features. I've been talking a lot about the height related roughness parameters, but width also plays a role, widths of peaks, and you can also do width measurements. But remember, with this technique, we're diffraction limited to about 200 nanometers. There are also some artifacts that could crop up in most, although not all, forms of 3D optical profilometry. For those of you who do photolithography, know these aren't wings on the edge here. These are actually artifacts of the imaging technique, because reflecting light off a flat surface is pretty straightforward. But when you've got a vertical surface or a near vertical surface in the high 80s of degrees, almost 90 degrees, then when the light comes down, the few photons that scatter off something on the surface and make it back, it's a noisy measurement. It comes from different points along here, and you may not get a very good measurement. So the software may just guess. And you may see this beautiful straight line, but that doesn't mean you're actually measuring it, because generally the software for whatever 3D optical profiler you're using will automatically interpolate and connect the dots between the few data points that it has. So if you're measuring the roughness or numerical parameters on a sample like this, you should mask out those artifacts. Speaking of artifacts, here's an example I took deliberately using focus variation on a really, really flat sample, which it looks almost like there's some hydrophobic surface here and it's in a pool full of water and the water is sort of beating around the edges in some really cool way. But actually, nope. It's a reasonably flat sample on a reasonably flat substrate. The instrument didn't really know what was going on there, so it ended up guessing and just filling in the blanks. So if your image looks weird, try some different imaging conditions to see if you can make it a little bit more sensible. And you can often make it work somehow, but on a few occasions it'll be really tricky to make it work and you might need to choose a different technique. One of them is if you have really, really short samples, or on the few nanometers in height, or if you have features that need to be resolved with less than that 200 nanometer lateral resolution. Then atomic force microscopy is very useful for this. A couple of other conditions that might suggest that you might want to try a different technique are if your sample is transparent and very thin and on a highly reflective substrate, like Julio showed earlier. But as he showed you, you can usually make this work. For those situations where you can't, a contact-based technique where you're actually touching the top surface means you're not going to be fooled by the optical properties here. A third, somewhat rare instance where you might not want to use it is if your sample is sensitive to the wavelength of the laser that's used to do the confocal measurement, which is generally a violet laser. So for example, if you have photoresist that's intended to be developed under ultraviolet light, it's still sort of sensitive to the violet light. So you can measure it, but if you use too much laser power, you will actually expose and damage the sample. So either don't use so much laser power or try a different technique. These are contact-based surface topography measurements, whether it's intermittent contact or constant contact. Atomic force microscopy is great for high resolution, and for more details on that, I'll point you to the first webinar in our series, which is a basic introduction to AFM. AFM and stylus profilometry are both touching the top surface of the sample so they don't get mixed up by index of refraction or laser wavelength effects. Stylus profilometry is most commonly done as a 2D measurement, which is exactly as straightforward and easy as it sounds. 2D, line profiles, stylus, dragging a diamond stylus over a surface exactly like a record player, and then you get a line profile. Because it's a 2D measurement doing just one line at a time, it is really fast. Instead of taking a couple minutes, it'll take a couple seconds. So AFM will give you excellent vertical resolution and much better lateral resolution because it's not diffraction limited. However, with AFM, you're limited to small fields of view and small samples. For 2D stylus profilometry, where you're doing a line, it is zippy, just super fast, but you get one line at a time. For 3D optical profilometry, you get really good resolution. And like stylus profilometry, you're not limited to small areas. If you stitch the images together, you can get extremely large areas. And a big advantage is you apply no force to your sample. So all of these techniques are good, and which one you choose depends on what you want to measure and the properties of your sample.
So in summary, the main strengths of the confocal optical microscope is profiler is that it's non-destructive. It can construct a 3D image from the sample surface, and in some cases interfaces as well, with a respectable resolution, especially in the axial direction, and present a large field of views when you're using image stitching. Its limitation, since it's a scanning technique, it can be slow, for example, when compared to some other techniques like interferometry or focus variation. Its resolution will depend on the numerical aperture of the objective that you're using. And if your sample is smaller than its diffraction limited lateral resolution, then that will be also a limitation in your case. So I would like to thank you all for attending our webinar today, and remind you that there are many more to come. The next one schedule is next Thursday at noon, when Jade Wang will talk about practical microanalysis based on scanning electron microscopy. I also would like to point that if you have any questions beyond the seminar about the 3D optical profilometer, these are the staff responsible for the instrument, and you can contact us at any time through our emails there. And finally, I wanted also to call your attention to another series of webinars that we are participating into, which is the Making the Best of a Bad Situation, a characterization seminar series. And that you can get more details at the go.illinois.edu MRL Big 4 webinars website. So thank you for your attention, and we're ready for questions that you might have.
Okay, thank you very much, Julio and Kathy, for the very good presentation. We do have a few questions here. The first one is for Julio. Can you comment on what types of samples would be better to be done with focus variation versus confocal versus interferometry?
Yeah, so if your sample is large, in general, to save time, you would like to do it on focus variation. If you're interested, like Kathy said, on the case of the O-ring, for example, on the very tiny little nuances of the interface, it's still better to do it in confocal mode, but it takes much longer time to do that because you're scanning the image. Between the confocal and the focus variation is basically question of speed, that you would choose one over the other. For the confocal, between confocal and interferometers, is sometimes you want a resolution that goes way beyond of what the confocal can do. And if you look at the, let me see if I can find that slide here a little quicker. This one, you can see that if you want a resolution that really goes down beyond 1 nanometer or below 1 nanometer, then you're better using interferometry. If you have samples that are too rough, this will not work, so then you're restricted to the other two. And if you have two dissimilar materials on your sample, it's tricky to do with interferometry as well. It's not impossible, but it makes your task much more difficult.
Thank you. Another question we have is, with the, obviously in focus variation confocal, how does the microscope determine what is in focus? Obviously when we use our eyes, we adjust, but how does the microscope do it? Is it a computer algorithm?
Yes, it is a computer algorithm, and it basically analyzes what is the frequency of the data in the picture. When the frequency of the variations there is much stronger, then you are in focus.
Okay, and one more for you, Julio, right now. In your opinion, are there any practical differences between the companies that offer microscopes with confocal pinholes versus confocal slits or windows?
I have restricted experience with different companies there. I tested Olympus, Keyence, and Zeiss when we were buying our instrument, and I liked them all, but there was some things that were better on one, some things that were better on the others. So it was really on the detail. When we had the SensorFAR demonstration in the lab, we loved the instrument as well. So it's on the details really for your application, and which one will give you the best thing. On the slit confocals, I'm not so sure. I haven't played too much with that on the 3D profiler analysis. We have a fluorescence confocal, that is a slit confocal, and Raman slit confocal, and then they operate very well, but a point confocal gets better resolution than those.
Okay. This is a question for Kathy. How do the results for thickness and mainly roughness, compare from this technique compared to other techniques like ellipsometry or X-ray reflectivity?
Well, one of the cool things about X-ray reflectivity is that you can see through surfaces comparatively quite easily. So that's the case where if you want to see roughness of buried interfaces, XRR can do it. As Julio showed, if your top surface is transparent, you can sometimes do it if it's transparent to the violet laser. So if that's a special need that you have to see through the initial layer or two of your sample, then you might want to choose XRR. Sorry, I got distracted thinking about how cool it is to see samples. What was see through samples? What was the rest of the question?
It was ellipsometry versus X-ray reflectivity versus these techniques for surface roughness measurements.
Like how small of a...
How do they compare? Yeah.
Well, Julio, would you like to talk about ellipsometry?
So ellipsometry is not the best method to determine roughness of your sample. It can be used as one of the parameters in the fit when you're feeding the data. But I wouldn't consider it a very accurate measurement of your roughness. I would always refer to a stylus profilometer or AFM if it is the top surface. If it is the interface, then I think do all of them, XRR and ellipsometry and this one, and compare the results that you get for each one of them.
Okay. Kathy, the sample that you showed with the pattern sample, can you comment on the image processing necessary to get rid of some of the edge effects on those samples?
The pattern sample, I believe, is the X-ray, or sorry, the AFM grading. And I'll try to bring that up here.
I am just getting that. Okay, you got it.
So if you want to exclude these particular areas, then you should choose a mask to go over top of those specific areas. Sometimes you can use the software to let the computer judge what is an outlier, but often it's generally easier and a little bit not much of a difference really to just do it by eye, because it's really apparent here. So what we did with this sample initially, and this is a very flat sample, only, let's see, 200 nanometers tall. So it's within the range that this technique can measure comfortably, but it's not always incredibly easy. So we took this image, and then when it was recorded, it was actually tilted because everything is tilted on the nanoscale. So we subtracted a plane from everything. And that's why this part and this part are all the same height in the color. And there's a little bit of deviation here in the middle, probably due to not having done the flat field calibration right before having done this. So when you're measuring heights on things like this, it's better to measure heights nearby to each other. If you're measuring widths, it's better to average over a large number of them, especially since trying to find where the edge of this is a little bit tricky. So masking will help all of your calculations ignore those regions there.
Okay, this is kind of related. I'm gonna question here. Once you've acquired a series of images, is it possible to automate the analysis, or is this always a manual process?
Yes, it's possible to automate the analysis. Almost every 3D optical profiler that I've used or tested has something in the software that allows you to do automation of the analysis. This is one of those instruments that goes between science and manufacturing as well. So a lot of people will end up using an instrument like this in an industrial environment where you're just doing the same thing, the same sort of sample over and over, and you want to have a repeatable protocol and just come out with a report on the first sample that you measure and the 500th sample that you measure and the 1000th sample that you measure, without having to pay some poor tech to sit there and do the same thing every time. So automation is a part of the software on most of these that you can buy.
Okay. You had shown that some significantly sized samples in the 3D optical profiler. Are there any particular issues that you have to deal with as the samples become larger and larger?
If your sample is outrageously heavy, then as the stage tries to move the sample, it might not move quite as smoothly. Generally though, as long as the distance that you travel up and down to do a measurement is within the working distance of the objective, and you're not hugely angled such that the objectives would bump into the sample, then you can generally measure anything relatively large. There is sometimes a little bit of extra mass if it's really, really heavy that affects stitching. But if you're just looking in one particular image and not moving the sample from place to place, then that part isn't a problem either.
Also on our Kians, the limit weight that the stage can take is about 6 pounds. So anything more than 6 pounds, and we had samples that were more than 6 pounds, we need to adapt a different way to measure them.
Okay. This question is, what range of roughnesses, for instance, our Q value, that the optical profiler can reliably measure without having to go to something like AFM?
Ooh, I like this one. The RQ value, if I say that the resolution of this technique vertically is generally around something like 20 nanometers, you might think that it can't really see very small RQs, but since RQ is smaller than the actual height of the feature, you can actually measure RQ in sort of the few nanometer range. It gets a lot more reliable if you're up in the sort of tens to hundreds of nanometers, but because this is not your surface feature height, but it's instead an average of the square of it, and then the whole thing is square rooted, it ends up being a smaller value that you can measure.
Okay. This question seemed interesting and followed along. Is it also possible to measure samples with high aspect ratios, such as like a nanowire array or a pillar structure?
Yes, as long as you don't care about the sides too much. You can definitely measure the heights, and I'll get back to this image here. You can definitely measure the height between the top surface and the bottom surface, as long as the spacing between the nanowires is larger than the resolution limit. So if they're 200 nanometers apart or further, because otherwise you might not be able to resolve the difference between the two of them and see that bottom part in between the two of them. But if they're far enough apart, yes, you can see them, but you'll end up with some weird edge effects. If you just want to know the height of them and they're wide enough that you can actually see the top surface of it, then yes, you can. Nano pillars are good. Nanowires, if they're a few hundred nanometers, or sorry, if they're a few nanometers, you won't be able to see just because of the resolution.
Okay. Here's a question. Can you comment about challenges for measuring the surface of a large transparent sample where the sample is several millimeters thick? What would be the challenges for that?
So several millimeters thick. The main challenge is that your film needs to be less than the working distance of the objective. So if you want to have very high resolution on and use a very, very high numerical aperture objective, you will be with a working distance on the order of 300 microns, 200 microns, and then you can only see films that are that thick. If you try to go to the surface, the interface below the top surface, you crash the objective on the top surface. So that would be a challenge for measuring large transparent or thick transparent samples, right? But you can, if you don't care too much about the roughness features, in a very, very small scale, you can use the larger working distance objectives. We have objectives with 16, 25, and 8 millimeters, and even one that is 3 millimeters. So if you are below those 3 millimeters, you can still see the other side of your film.
And if your surface features are fairly large that you're interested in, and your main worry is that your sample is transparent, you can actually sort of sprinkle something opaque on top, like baby powder even, if you've got very large surfaces that you're trying to measure, very large features on your sample. Of course, that will start to affect things if you're trying to get really high resolution images of that top surface. But if you can make the top surface of your sample opaque, then that will work. If you have an extremely thick, transparent sample, that might actually help compared to a thin, transparent sample, because you don't have, the software will sort of give up before it sees the substrate underneath. Although hopefully it will give up before it rams the objective into the sample.
We have a pair of questions here concerning instrumentation. One is, can you comment on the accessibility of different techniques and how much they cost? And the second, is it possible to do Raman and photoluminescence with these types of 3D optical profilers?
Okay, so our optical profiler and all the ones that, actually not all the ones that we saw, one of them could do fluorescence at the same time that you do optical profilometry, and that was Zeiss. The other ones didn't. I'm pretty sure Olympus could maybe adapt something to there. I know that Keyence has a fluorescence microscope as well, but it's a different fluorescence microscope. It's not Confocal as far as I know. I need to check again on their website. But I don't remember. Ours don't have a fluorescence or Raman on it, so we cannot do the same there. But we have a Confocal Raman and a Confocal fluorescence microscope, and both of them can do those techniques and in 3D, so you can see the fluorescence across the volume and the Raman across the volume of your sample, given that your sample is transparent and you get signal from inside it. But they're not designed for the 3D profilometry, and they are slower in getting this topography data.
Okay. This last question deals with different fields of view. When you take images with different fields of view, you'll often get different results for roughness parameters. Typically, lower values, RARQ, occur with a smaller field of view, higher magnification. What would you recommend in order to determine the roughness value of a sample, assuming the feature size observed by these different magnifications is used?
The real way to do it is to take a series of images with the same number of nanometers per pixel. So let me see if I can find my slide about this. The same number of nanometers per pixel is, for example, these two panda images. They're at the same resolution, and the field of view on this one is smaller. So this particular image on the left is potentially, it's having a problem measuring the panda roughness because there's a large tree in the area. But on the right, you have a larger field of view, but the same resolution. So you're getting the same quality of information, but over a larger distance. So if you were to just switch from the small field of view to a large field of view, but keep the same number of pixels, then suddenly this, let's say, 100 pixels is spread out into a distance that's like 5 times as large. So you essentially cut your pixel resolution by a factor of 5 in that particular example. So the way to figure out what the optimal field of view and optimal resolution is to start with a small image, small field of view, reasonably high resolution, increase the field of view size while still keeping the number of nanometers per pixel the same, and then keep doing that until you get a large enough image that your answer doesn't change as you increase your field of view. There are 2 downsides to doing it that way, which is the quote-unquote right way to do it. Downside number 1 is the more pixels you have, the slower it goes for techniques that scan anything, like AFM, which scans the tip, or confocal profilometry with a point source where it has to scan the point. It will take longer to do a larger number of pixels. At some point, you'll also end up being limited by just how many pixels are in your detector. So there will be a limit to that. But at a certain point, as you start increasing the field of view, you'll start running into different features like the waviness here. So the problem that the person asking the question brings up really well is that as you are increasing your field of view, you'll also potentially capture different types of roughness on your sample because you are exposing yourself to different sample areas that maybe your initial field of view was too small for. So that's the right way to do it. The not really officially the right way, but what I see a lot of people doing if they want to do comparison is find a good field of view and a good number of nanometers per pixel and then be consistent across samples. But that's not an absolute number. I think the questioner was asking, how do you find sort of a more intrinsic value? And for that, you do want to slowly increase your field of view while keeping the same number of nanometers per pixel.
All right. Well, I think we've actually run out of time now, but I wanted to thank our speakers again, Dr. Soares and Dr. Walsh. And if you could go to the last slide real quickly, I would like to invite everyone back next Thursday for the next presentation by Jade Wang on the practical microanalysis based on scanning electron microscopy.
Thank you.
Thank you.